Hi everyone, welcome to the third lecture on Chapter 3. Today we are going to cover specific heat capacity. And specific heat capacity tells us things like, in looking at this pot of water that we can say is on the stove, or maybe pot of soup, it will tell us kind of which things will heat up faster or slower, and that's all based on the specific heat capacity. So if you think about heating just a pot of water on the stove. Maybe you're going to make some pasta. The metal pot heats up really, really fast because metal has a really low specific heat capacity. And the water heats up really, really slowly because it has a very high specific heat capacity. So kind of like in this picture, if you look at the metal spoon has a lower specific heat, so it heats up really, really fast. But the wooden spoon has a higher specific heat, so it heats up much slower. The wooden spoon can absorb much more energy before it changes temperature than the metal spoon can. So this is what we're going to talk about today. So the specific heat is different for different substances. And you'll hear me say specific heat or specific heat capacity. They mean the same thing, but they're different for different substances. And it's the amount of heat in either joules or calories. We are typically going to use it in joules. And it's this amount of heat needed to change the temperature of 1 gram of any substance by 1 degree Celsius. We talked about last time that the technical definition of the calorie was the amount of heat it took to change 1 gram of water 1 degree Celsius. So this is the amount for anything, right? The specific heat for anything. 1 gram of that by 1 degree Celsius. And in the SI system, we use joules per gram degree Celsius. So it's essentially like this, joules per gram degree Celsius. Okay. So to calculate specific heat, we have a formula. Q equals MC delta T, or like we used to say, Q equals MCAT, because the delta kind of looks like an A. So Q stands for heat in joules. I know that it should be H, but H, lowercase h is Planck's constant and uppercase h is enthalpy, so they've already been taken by chemistry. So we use Q. So that's heat, and that will always need to be in joules. If it's not in joules, you'll need to convert it into joules before you can use it. M is the mass, and that's always going to be in grams. So again, if it's in kilograms or something like that, you'll need to convert it. C is the specific heat, and that's something that you will always be given or need to look up, and it's in joules per gram degree Celsius. This whole thing, joules per gram degree Celsius, that is the unit for specific heat. And then delta T is the change in temperature. So you may have a scenario where it says it started at one temperature and it finished at another temperature, and you need to do the change, and so you'll end up subtracting them. In chemistry, just in general, this triangle, this delta, we're going to see this again. That always means change. So that tells you might need to subtract 2 different temperatures or subtract 2 different pressures or volumes or whatever the case may be. But delta T is how much the temperature changes. And so we have all of these substances. So here we have aluminum, copper, gold, right? And we're typically just going to use this column, this joules per gram degree Celsius column. And like I was talking about on the very first slide, metals tend to have a really low specific heat, which means that it only takes a little bit of energy to change the temperature a lot, right? A little bit of heat will change the temperature a lot, whereas something with a really high specific heat like water, I know that that doesn't seem that high, 4.184, but if we look at and we compare it to like iron, right? The specific heat for water is almost 10 times higher than the specific heat of iron, which means that iron will heat up almost 10 times faster than water will, which is crazy. So that's why your pot, which is made of metal, maybe it's made of aluminum or whatever the case may be, but the pot will heat up really, really fast because it only takes a little bit of energy to change the temperature a lot, whereas water can absorb a lot of energy before it changes temperature very much. This is one of the reasons, and like I'll say it on this slide, this is one of the reasons why water is used as a coolant, like in your car, because the water can absorb a lot of heat before it changes temperature. So we would want to use something like water as opposed to something, I don't know, that's got a lower specific heat like ammonia or ethanol, besides other problems associated with using those. But the higher the specific heat, the more energy your substance can absorb before it changes temperature. And so if we're using water as a coolant, the goal would be to keep it cool. So we'd want it to be able to absorb a lot of heat before it changes temperature. So this is another example. Large mass of water near a coastal city can absorb or release 5 times the amount of energy absorbed or released by the same amount of rock near an inland city. And again, this is because water has a really high specific heat. So essentially what this all means, what the really high specific heat means, is that it takes a lot of time to heat up, and it also takes a lot of time to cool off. Because once that water has absorbed all that energy, now it has to release it, but it has a lot of energy in it. So it will take quite a while for all of that energy to leave. So water takes a long time to heat up and a long time to cool off because it has in it really, really high specific heat capacity. So let's try to do a problem. So this says calculate the amount of heat released when 7.40 grams of water cools from 49 to 29 degrees Celsius. And it says water specific heat is 4.18 joules per gram degree Celsius. These specific heats you will never need to memorize. You will always be given them. You might actually start to recognize the one for water because we use it a lot, especially if you go into higher levels of chemistry, you'll use that quite a bit, but you're never going to have to memorize them. So we have Q equals MC delta T, right? That's our equation. As soon as you see, we're talking about heat and changing temperatures, you're like, that's a Q equals MCAT problem. So we have a lot of information given in the problem. We have 7.40 grams, which is the mass. We have 2 temperatures, and that tells you that you're going to need to subtract them to get the change in temperature. And we have the specific heat. So if we are going to outline our variables, we go Q, M, C, delta T. Okay, so Q is what we're trying to find, right? It says calculate the amount of heat. That is what we are looking for. We're looking for heat. We're looking for Q. Our M value is 7.40 grams. And remember, your mass always has to be in grams. If it's given to you in something else, then you'll need to convert it into grams before you can solve. C is our specific heat. So that's 4.18 joules per gram degree Celsius. And then our delta T is our change in temperature. So when we have 2 temperatures, we need to know how much it changes by. So we'll do 49 minus 29, and that will get us that our delta T is 20 degrees Celsius. So now we're looking for heat. So we need to rearrange our equation to solve for heat, but it already is. Q is by itself on the left here, so we don't need to rearrange our equation in this case. If we were solving for M or C or delta T, we would need to rearrange our equation. But since our equation's already rearranged, we can just go ahead and plug in the numbers. So here's our M, our C, and our delta T. So we'll just multiply all those together and we'll get our answer. So pretty straightforward in this case. Our units for Q are always going to be joules. Here's another one. This one says, what is the specific heat of lead in joules per gram degree Celsius if 57 joules raises the temperature of 35.6 grams of lead by 12.5 degrees Celsius? So again, we're going to outline our variables, Q, M, C, delta T. So Q, right, we're looking for joules, so that's here, 57 joules. Our M value is always in grams, so that's going to be here, 35.6 grams. Our C value is what we're trying to find, where it says what is the specific heat, so we're trying to find specific heat. And then our delta T value, it says it raises the temperature by 12.5 degrees Celsius. So that is already telling us our change in temperature. It's saying it's changed by 12.5. So we don't need to do any subtraction here because it's not telling us our initial and final temperatures. It's already telling us how much it's changed by. So after we have all of our variables, now we can go and rearrange our equation. So we have Q equals MC delta T, and the way that we're going to rearrange it is we're going to divide by anything we don't want next to our C value, which is what we're trying to find. So we're going to divide by, right, and we don't want M over there anymore, and we don't want delta T over there anymore. So we're going to divide by both of those. So then the M's are gone, those delta T's are gone, and we're left with C by itself. So up there we have Q over M delta T equals C. And I like to just switch the sides because I like to have the variable that I'm solving for always on the left, but you could leave it that way if you like. So C is equal to Q over M delta T. Then you can just plug your numbers in. So our 57, right, that was our joules. And then our mass is 35.6. We have 12.5 degrees Celsius. So we'll do 57 divided by 35.6 times 12.5. I would go ahead and multiply these together first, the stuff on the bottom, before you plug it in. And then you'll get your C value, 0.128 joules per gram degrees Celsius. Let's try another one. So this one says how many kilojoules are lost. So this is different, all right? We're gonna have to have our answer in kilojoules, which means we're still gonna solve for Q, right? But Q is in joules. So after we get our answer in joules, we'll convert joules into kilojoules using those conversion factors like we've done before. So we're starting to combine things that we've learned. Okay, so it says how many kilojoules are lost when the body temperature of a surgery patient with blood volume of 5,500 milliliters is cooled from 38.5 degrees Celsius to 33.2 degrees Celsius. So assume that the specific heat and density of blood are the same for water. Okay, so that means we know that the specific heat is 4.18 joules per gram degree Celsius, but you should say, hey, hang on, why do we have a volume? We haven't had volume in any other problems, right? We have, we have specific heat, we have this will end up being our delta T, and then we have a volume, but we don't want volume, we need to have grams, right? The density of water, if you'll recall from earlier lectures, is 1 gram per milliliter. So that means anytime you have a volume just of water, not of other stuff, but if you have a volume of water, which we're assuming blood is mostly water, then you can use that as mass. So if it's 5,500 milliliters, that means it's 5,500 grams of water. Okay, only for water though, and it's because this density is 1 gram per milliliter. If it was anything else, we couldn't do that, but since blood is mostly water, we are going to treat it as water, so our volume and our mass are essentially the same. So now we have, right, we're going to outline our variables, Q, M, C, delta T. So Q we don't know, and I'm going to put a note here that I want my answer in kilojoules, not just joules. And then our mass is that one that we've converted, right? We had volume, but now we're going to use it as our mass. So that's in grams. Our C value is 4.18 joules per gram degree Celsius. And our change in temperature we have to calculate because we have an initial and a final temperature, right? We have two temperatures, so we're just going to subtract them, and that gets 5.3 degrees Celsius. So now we have all of our variables, and we can go ahead and solve for Q. Since the equation is already solved for Q on the left here by itself, we don't need to rearrange our equation, and we can just plug things in. So we have M, C, delta T, and we can just multiply them all together and get our answer. And so normally we would be done, right? That's our answer in joules. But we need to convert our answer from joules into kilojoules. So we'll put that number at the beginning of our train track here. And we know these, this equality. 1 kilojoule is equal to 1,000 joules. And we can write our two different conversion factors, one with joules on the top and kilojoules on the bottom, the other with kilojoules on the top and joules on the bottom. And then we have to figure out, okay, which one do we use? Well, remember we always have to cancel our units down and to the right. So if we have joules on the top there, we are going to need joules on the bottom, which means we're going to use this one here on the right. So 1,000 joules will go on the bottom, 1 kilojoule will go on the top. Double check that our units cancel, and we're left with kilojoules here, which is what we were trying to find. So then we can just do 121,847 times 1 divided by 1,000, and we get 121.85 kilojoules. And just as always, remember to multiply the top and divide the bottom. Okay, using what you've learned from this lecture, go ahead and find your Chapter 3 lecture worksheet